Good morning. This is a new experience for me, being videotaped. Professor Roble is not here today. He's feeling ill, so you've got me for the day. Well, first of all, congratulations. You're now starting reflection and refraction. You've made it through the hard part of Physics 250. Okay, the rest is a cruise. All right. But the equations aren't particularly hard, nothing like what you've had to do for like Gauss's law and magnetism and stuff like that. Okay, but the only thing that you have to be pretty good at is basic geometry. That's about it. So if you're a little bit weak at that, you might want to review it. Let's do something fun today. This is one of my favorite demonstrations, so pass this around. Okay, you've got a series of mirrors in here, like so. And you've got a small little pink pig at the bottom. The combination of the mirrors causes the image of the pig to appear right here. It's pretty old, pretty dusty, pretty scratched up when it's new, okay? It's really cool. The pig looks like you can reach out and touch it. Why don't you pass this around and try not to tilt it too much so that the pig moves out of the center. You may have to redo it. And just lift up the lid and recenter the pig. So, some basic physics, but some pretty hard stuff. And we don't have time, or really, and you don't have the mathematics yet, though I'm sure you've got the intellect. It's just a question of not having the mathematics to really derive a lot of the equations that we're going to be using. This is really more senior level, introductory, graduate level stuff. But let's think about this, okay? You've got a surface, a nice flat surface. Maybe it's glass, maybe it's water, but you've got air here, water here. All right, and we call this medium 1 and medium 2. And you've got a ray of light. I'm going to use this red marker to indicate that. The ray of light comes in like this at an angle, hits the water. And something really kind of nice happens. You all know the physics of this. You've probably looked at things ever since you were a little kid, noticing that things under the surface of water appeared somewhat differently. What's going to happen is part of the light is going to reflect off the surface of the water. We refer to that as the reflected wave. And another part is going to be transmitted. And what we see here, and probably if you thought about things, this would seem pretty reasonable. We define these angles. Theta 1 prime, and theta 2. Now, in an upper level electricity and magnetism class or an upper level optics class, one of the things that you figure out is the ratio of the amount of light that's reflected versus the amount of light that's transmitted. All right? But some of it will be reflected, some of it will be transmitted. The reflected stuff follows the law of reflection. Theta 1 equals theta 1 prime. Pretty nice, eh? The law of refraction N1 sine theta 1 equals N2 sine theta 2. This is also known as Snell's law. Now the ends are called indices of refraction. So usually the lectures are a bit behind the labs, so I wouldn't be surprised if already in your 250 labs you've had to measure these. Is that right? Okay. All right. It's a pain, isn't it? Not measuring it, but it's a pain that the labs are ahead of the lecture. All right, so you've measured these. And there's a lot of really good physics involved in this simple indices of refraction. Okay, so these are, first of all, they're frequency dependent. All right, that leads to some interesting things later on that we'll talk about. Part of a big challenge during the 70s and 80s was communicating with submarines. All right, and it's still kind of a challenge too, a technological challenge. So, do we have many electrical engineers here? Okay. Do you know what the challenge was? All right. The problem is that water also attenuates the signal. Okay. So you learned probably in previous lectures that light is an electromagnetic wave. And human beings are only sensitive to a small portion of the electromagnetic spectra, just between what? About 400 and 700 nanometers in terms of wavelength. And you've got that fundamental equation that says that the wavelength times the frequency is equal to the speed of light. All right. Problem is, you want to communicate using radio waves with a submarine, but as you try and send radio waves through the water, they get attenuated. All right? So a big problem is trying to understand the attenuation as a function of frequency, the index of refraction as a function of frequency. There's an awful lot of good physics in this and good engineering as well. What they did is they found that the best way of doing this was to use extremely low frequency signals, but low frequency required big long antennas, spanning the length of the Upper Peninsula of Michigan. So some big technological challenges for engineers and physicists with regard to this. All right, so this index of refraction, you measure it experimentally. And we relate it to the following, that n is equal to the speed of light in vacuum divided by the speed of light in the material. So for air, n equals about 1.000293. No big deal. All right. So let's just call that 1. But for water, n equals 1.33. So that means the speed of light in water is significantly lower than the speed of light in air. For diamond, n equals 2.419. Even more higher. Okay, so the speed of light in diamond is about half that in vacuum. Okay, so compared to all the stuff that you had to do to get here, you had to go through Gauss's law and Ampere's law and all that hard stuff, okay, with AC circuits within resistors, inductors, and capacitors. This is the diagram that you have to memorize. And these two simple equations. Nice, isn't it, compared to what you've done? All right. There's one more thing, all right. Electrical engineers and sometimes physicists find themselves working as process development engineers. And one thing that they work on is, for example, thin film coatings. All right? And thin film coatings are really important in the manufacture of good optical equipment, stuff like that. So there's one more bit of physics. You've got the following. You know that the speed of light in a material is lower than that in vacuum. And you also have that fundamental equation, okay, and when I say fundamental, I mean the following. It ought to be a part of you for the rest of your life. We don't just simply study physics just to pass exams. We acquire that knowledge so that we can use it for the rest of our lives. Your employers will expect it from you. And that fundamental equation is this. Lambda, the wavelength, times the frequency is equal to the speed. And so now, the speed of light in a material is lower than that in vacuum. So what changes? Well, it's a 50-50 chance, right? It's either the wavelength that changes or the frequency. But it turns out that it's the wavelength that changes. So in materials, like water, the wavelength changes. And so the new wavelength, lambda, well, let's think about this. Let's rewrite it the following way. Lambda prime, the new wavelength, times the frequency will equal the speed in the material. That's going to be the speed of light divided by the index of refraction. So the lambda prime equals the old lambda in vacuum divided by n, the index of refraction. So your new wavelength in the material is shorter than the wavelength in vacuum or in air. It's important to remember this. It's a key business when you get to try to understand optical coatings. Anyone do any time in the military? All right. Okay. I once had one of the probably worst jobs to have in the military is to be a forward artillery coordinator or spotter. Okay. You're given a good pair of binoculars, and your job is to do what? It's to call in artillery on the other people. Now, the other people probably don't like you doing that. So what's their idea? They'd like to kill you. All right? They'd like to call in artillery on you. So one of the things that artillery spotters are given, forward observers, they're given really good binoculars with really good optical coatings to prevent reflection. So when light hits the binoculars, it's not reflected back and nobody notices, oh, there's a guy with a pair of binoculars over there. All right? So they're issued really expensive binoculars with really good optical coatings to minimize reflection. And you'll learn about those in about a chapter or two, how that's done, the physics behind that. I was once teaching this class many years ago, and there was actually a forward observer, and that was probably the only thing he was really interested in, was that bit of the lecture. It was life and death to him. All right. So given this, Let's now work a problem. The problems aren't particularly hard in this chapter. Again, you've made it this far. The rest of the semester, pretty easy. Like I say, it's just a matter of just knowing those equations, the diagram, and good geometry. So let's do a problem here. And one of the key things is really just making a good drawing, make it big. I tell students in my class that paper is cheap. Tuition is expensive. All right, so let's do this. Common problem. You've got a plate of glass, nice flat plate. It's got a good thickness to it like so. I'm trying to draw these lines parallel. Draw this perpendicular. All right. So here we have glass. We've got air here and air at the bottom. And we want to know what a light ray is going to do as it goes through. So we're going to draw our light like this. It hits here. This is going to be theta 1. It enters into the glass. Part of it is reflected. Let's not worry about that. It comes down like this. Theta 2. And then what happens here? Part of it is actually going to be reflected at this surface, but part is going to be transmitted as well. If this is theta 2, then what's this angle in here? See, I told you, this is where you want to have your geometry, down pat. Okay, if this is theta 2 here, and this is 90 degrees, this is 90 minus theta 2 in here, and so this has to be theta 2 there. Happy with that? Well, if this is theta 2 here, then what happens is the following. You've got n2 sine theta 2 here has to equal then n1 sine theta 1 at the bottom. So what happens is that when it comes out like so, theta 1, and this theta 1 is the same as that theta 1 there. But now if we look at this, this isn't maybe the best drawing, let me put it like this. We see that it's displaced. That if we drew this line all the way through, that this line comes out parallel to it, but displaced a certain distance. All right? And so the classic problem, and don't be surprised if you see this on one of Professor Robles' exams, okay, is to calculate this distance, the distance between here and here, the amount that this ray is displaced. Let's try and use colors to indicate that. All right, I've got this line, this green line. That's the thickness. I'll call that T. I want to find this red line right here. All right, I'm going to call this D. I want to find it in terms of the indices of refraction and stuff like that. Okay? Let's try and figure it out. It's a good test of your geometry and trig. Okay? Well, we got to work on this a bit. All right? Let's figure it out. Let's do this. Let me erase this line right here. Okay? And draw it in black. All right, I'm trying to keep my colors straight. You know the thickness? you know this angle theta 2. All right? Let's think about one thing in here, and I'm going to use D for this. This angle right in here. This angle right in here, the little red one, is what? It's theta 1 minus theta 2. So this angle, theta 1 minus theta 2. I'm going to call this black line L. So if I had L, then D would equal what? In terms of theta 1 minus theta 2. This would be the hypotenuse of a right triangle. So D would equal it would equal the sine of theta 1 minus theta 2 times the thickness. Times this length L. We okay with that? All right. Now, how do we get that length L in terms of this thickness T and this angle theta 2? So here we have that L, or rather the cosine of theta 2 is equal to the adjacent over the hypotenuse. So that's equal to, and it's equal to keeping my colors right, it's equal to T, which I know, divided by L. So L equals T divided by the cosine of theta 2. So finally you have this. You have that D, just working through the geometry and the simple equations and the little bit of trig, D equals T over the cosine of theta 2 times the sine of theta 1 minus theta 2. If you work through things slowly, remembering your basic geometry, your basic trig, you'll do fine. Okay. And nature is really rich and wonderful and complicated. And the complications are some of the things that produce the wonders of it all. All right? We have this thing called dispersion. The index of refraction is a function of wavelength. And if we were drawn, and let's see, so you can measure that, for example, experimentally by sending light of different wavelengths through a material. One of the big challenges, if you go on to upper level graduate physics and you take a course in solid state physics, you'll calculate the index of refraction as a function of frequency for different materials. It's an important challenge. But let's give some examples. See what we're doing. Okay, so let's see. This is figure, or part of it is figure 35-21 from your textbook. If you look at something like this, starting off with a wavelength of 400 nanometers, and by the way, these wavelengths are for the light measured in vacuum, going to 700 nanometers like so. What you see here, for example, by the way, if we're at 400 nanometers, what color light is that? Approximately. So people should be able to, and you want this for your own benefit, to be able to associate things, wavelengths, with particular colors. Okay, actually this is more violet. Does that normally happen? Oh, okay. Okay. All right. And this is red on this side. Okay. All right. And so what you see, for example, okay, if you've got something like crown glass, and you'll see the following. It'll start out at about, let's see, at the violet side, it'll start out about 1.53 and drop down to about, okay, 1.51, okay, at the red. Not much of a change, okay, less than a couple, less than, a percent or so, okay? Well, on the order of 1%, but it makes a big difference, okay? So if you have ever played around with prisms when you were a little kid, that's the effect that you're seeing, all right? Anyone want to learn something vaguely romantic? Impress a girlfriend, boyfriend, whatever? Okay, something that you might find useful later on in life? The following thing, all right? Air also has a little bit of a dispersion to it as well. Okay, so for example, if you would look at the surface of a light bulb, okay, through a prism, you'd see that the top surface of the light bulb looks a little bit blue, then green, then yellow, and then red. All right? Well, let's see. You're all in this so that you can have really good careers, make lots of money. All right? Fair enough? Fair assumption? Okay. So now how many of you, once you're making lots of money, you plan to treat yourself to a good vacation? How many? Okay, where would you like to go? Anyone want to go to the Caribbean? All right, great. Okay, so you go to the Caribbean, all right, and you're watching the sunset. And as the sun sets over the ocean, the atmosphere can act like a prism. And so as the top of the sun is just about to disappear, okay, below the horizon, it's like that light bulb through the prism. It should look blue at the top, but the problem with the blue color is that it's scattered by the Earth's atmosphere. So the top of the sun should look actually green. And sometimes, just as the last little bit of sun is about to disappear below the horizon, you'll see this green flash of light. All right? So it's something to look for when you're on that Caribbean vacation. All right? Now, there's a Scottish legend that says that anybody who sees that green flash will never be deceived in matters of the heart again. It's a useful thing to have, you know. All right. This business of dispersion also explains rainbows. Dispersion, reflection, and refraction. You know, it's strange, but we know why. And we've known since, do you know who was the first person to explain the rainbow? It was Descartes. The guy who gave us the Cartesian coordinate system. Same guy. All right? Now, it's funny, but I think that once we know something, it doesn't matter if we know it individually, it's just that if all of mankind knows it, it loses a little bit of interest. All right? People didn't know, for example, how the sun worked until the 1930s. Imagine not knowing that. Looking up at the sun, knowing that it gave you heat and light, but not knowing what happened. Wouldn't that bother you? All right? It bothered people a lot, and then they figured it out, and all of a sudden it doesn't bother anybody, because as long as somebody knows how it works, that's okay. All right? So here's the deal with the rainbow. All right? So if we take a water droplet, like so, and let's put two of them up here. Let me get this right. All right? If it's one way or the other, chances are I'll get it the other. I'm the kind of person that shows up at a stoplight, green. Okay, that means one thing. Which is it? Stop or go. All right. Okay, here it's like this. So let's draw two raindrops at different. Now, when you're looking at a rainbow, where's the sun? Well, okay, now you're here, you're looking at the rainbow like this. The sun is actually back here. So if you want to see a rainbow, all right, you turn your back to the sun and look around. What you'll do is you'll have raindrops like this. Now, if you've got red light, let's see, where did I put my red marker? Right here. Comes from the sun, you'll have a combination of red and blue. It hits in here, bounces off that, so you've got refraction at this surface, reflection here, refraction here, and hits your eye like this. The blue light will do the same, but due to the dispersion, it'll be hitting and not be as much. So you'll see the blue here, or the green, then the yellow, well, violet, blue, but I don't have a violet marker, blue, okay, green, yellow, and then red like this. All right. Now, the other stuff, the sun gives off white light. This light will be reflected differently and will miss you. So when you see this, you'll see the colors. All right. I was really fortunate in that I had a really good master's advisor named Bob Greenler, and he was like a second dad to me. And he was really good at imparting not just knowledge, technical stuff, but outlooks and attitudes that I'd need to be successful later on in my career. So I'm going to end this guest lecture a little bit early with the following story that I hope you'll remember. All right, so Bob liked rainbows and other optical phenomena. There's another thing, okay, called ice crystal halos. All right, and so if you look up at the sun sometimes, what you can see is a brilliant, beautiful ring completely around the sun at about 22 degrees. So that would be about, if you held your hand up like this, put your thumb on the sun, your little finger would hit the edge of that halo. Has anyone ever seen one of those? Okay, you're missing something good. All right, and Bob was into researching stuff like that as sort of a sideline to his work in infrared spectroscopy. And he thought, one day, he said he was sitting on his porch trying to avoid thinking of a problem. He never told me what the problem was. That was irrelevant to the situation. But he said this, I started thinking about rainbows. And it occurred to me that the human eye is only sensitive to a certain portion of the electromagnetic spectrum, between 400 and 700 nanometers. So the question is, are there rainbows out there that the human eye can't see? All right? And so he decided, well, how would I see one? Well, you'd want to look outside the spectrum. So at the low end, okay, you've got ultraviolet. At the high end, beyond red, you've got what? Infrared, which is heat. So what would be the easiest thing to detect? Heat, okay? So, believe it or not, there's infrared sensitive film. And nowadays there's a lot of infrared, night vision goggles and stuff like that that operate in the infrared. Though you really wouldn't want to, okay. Well, yeah, I don't know if you could use them during the day very well or not to see this. But so what he does is he goes out and he buys himself some infrared film. And now he needs a rainbow, so he takes a garden hose, strings it up, punches a bunch of holes in it, and if you've ever been watering your lawn and seen the rainbow in the water, you know what I'm talking about. And so he starts varying the settings, but actually there's a problem, all right? That infrared sensitive film is also sensitive to the visible light. So he needs a filter that will filter out the visible light but allow the infrared light to go through to the camera lens. So the Mark I filter, a black plastic garbage bag that's taped over the lens. It works. If you've ever held your hand out to grass clippings that were decomposing inside a plastic garbage bag, you could feel the heat, the infrared radiation going through. Varies the settings, takes pictures, sure enough. He can see the infrared part of the rainbow. So then he goes out, more infrared film, now a genuine commercial infrared filter. He's driving down the road, okay, sees a rainbow, he's got the camera, he's got the filter, he's got the film, steps out of his car, takes a few pictures, has it developed, writes a short article, makes the cover of Science, which is one of the most prestigious journals, all right? So there he was. He was the first person to take a picture of the infrared part of the rainbow. Now, when you really think about it, anybody with a high school background in physics could probably have done the same thing. All right? But he did it first. And the lesson that I learned, which helped me a lot, and every time I'd make a major discovery of my own, sometimes I'd call my thesis advisor and say, thanks. What he taught me was the following, that there's all sorts of really good experiments that are still waiting to be done, and that if you look at things with a good, fresh outlook, and you think, yeah, there's something here that I could do, chances are you'll be able to do it. All right? So there's lots of really good physics and really good discoveries that are still waiting to be made. All right? Well, that's it for today. Thank you. Professor Robles should be back tomorrow.